I hope you all have enjoyed the extra day to get your homework done. One quick announcement. There was some sort of mishap in Brightspace with grading homework 2. So for some reason it maxed out the score at 43 out of 50. So if your score is displaying 43 out of 50, please double check to see if that is the grade that you should have gotten by adding up all your points. And if you're say, hey, I earned more points than this, just submit a regrade request. And we'll get that fixed. For some reason, Brightspace decided to, again, cap out the scores at 43 out of 50. Not sure why. It was probably caused by a person. You should always get some written feedback. Usually, if it's graded by like Sophie or Kushagra, they just upload a document. Boyu and I will mark on the document you submit. So yours would have been graded by Kushagra. He usually uploads a document. If you don't see a document uploaded as part of your feedback, then just send an email to him and be like, hey, where's the document with my graded homework? Everyone should be getting graded feedback. If you aren't, we're either having trouble accessing it on Brightspace or it was forgotten. When you're grading 120 assignments, it's very easy to forget to upload any individual's grades. It's surprisingly hard to keep track of everything. Before we begin, do we have any questions about Laplace transforms that we've covered so far? All right, let's go ahead and get started. So we talked a little bit about the motivating the Laplace transforms, why we want a complex frequency basis in order to capture the steady state and transient responses to our circuit. We said this is the most powerful and fastest circuit tool we're going to work with. We looked at the application to ODEs. We learned how if you take a Laplace transform of a derivative, you get something that's like S times the Laplace transform minus any initial conditions. And then we looked at some Laplace transform pairs of some simple signals. And this allows us to go back and forth between, the Laplace domain and the time domain. So this delta function, Laplace transforms to 1 with a region of convergence of all of S. The unit step function, Laplace transforms to 1 over S, regions of convergence, real part of S greater than 0. Ramp function, Laplace transforms to 1 over S squared. E to the negative AT U of t, Laplace transforms to 1 over S plus A with a special region of convergence. Cosine of omega naught t U of t, Laplace transforms to S over S squared plus omega naught squared. And sine of omega naught t U of t, Laplace transforms to omega naught over S squared plus omega naught squared. So now, today we're going to talk about Laplace transform properties. And with these properties, we're going to expand our Laplace transform table to include many different functions, combinations of functions that we might encounter. So, and with that, we should be able to Laplace transform most signals that we encounter without a hitch. Remember, we can always use the definition of the Laplace transform for a given signal, should that be required. But these properties allow us to get Laplace transforms of harder signals, given that we know how it works on a simpler signal. So we discussed the definition of the Laplace transform, how it acts on time derivatives, and its linearity. So we're going to add 4 properties: frequency derivative property, time shift property, frequency shift property, and time integration property. So the frequency derivative property. We'll start with a time domain function and multiply it by t. This should be reminiscent of having repeated root solutions to our ODEs. Remember when we have, repeated roots, we introduce, t multipliers, multipliers of t from the power series of t. Also remember, if we had a particular solution that matched one of the roots of our characteristic equation in form, then we also needed that t multiplier or a higher multiplier of t. So here's what we're going to do. We'll say Laplace transform of t times f of t is, by definition, integral from 0 minus to infinity of t f of t e to the negative st dt. And then we'll say that's equal to integral from 0 minus to infinity of f of t times quantity t e to the negative st dt. So there we've just moved things around. And we'll say, hey, this t e to the negative st is like taking the negative derivative of e to the st with respect to s. Huh, okay. That's just how it looks like. So we're going to, do some, mathematical trickery that mathematicians hate, but engineers love. And we'll say that if long as f of t is well behaved, we can just swap the order of the integration and the derivative. And we notice everything in brackets looks like the definition of the Laplace transform. So we get that t times f of t Laplace transforms to negative dds of f of s, with a region of convergence the same as f of s. This is really handy because we can think of a lot of signals that we might want to put there. So t to the n f of t, just generalizing a little bit, is the negative nth derivative with respect to s of f of s. If f of t is u of t, t to the n u of t Laplace transforms to n factorial. That's not n, but really excited. That's n factorial, which is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, over s to the n plus first power. And then we might do t to the n e to the negative at u of t is equal to n factorial over quantity s plus a to the n plus first power. And, we might do something similar for like the cosine function times a t multiplier or a sine function times a t multiplier. Those you can work out as you need using this property. So already we've extended our knowledge of how Laplace transform works to a whole bunch of different functions that we're already anticipating seeing from ODE solutions. So what questions do we have about this? We still have not reached our threshold voltage of students yet. Go text your friends, tell them to show up to class. Hearing no questions, I will say you will get a table of Laplace transforms properties on the exam, where it'll tell you, this like little stuff at the bottom, and that's boxed. Tf of t is, Laplace transform negative dds f of s. You probably won't see any proofs of Laplace transform properties. It's up to you to figure out how to apply these properties, though. So you need to have the basic functions, which will also be given to you in a table, as well, to know how to use them. So keep that in mind. We're going through a little bit of the derivation here just to motivate what's happening. You will receive these in the table, though. So the next property we're going to talk about is the time delay property. So let's say we have the Laplace transform of a function, and we delay it when it happens by t naught. So Laplace transform of f of t minus t naught equals the integral from 0 minus to infinity of f of t minus t naught times u of t minus t naught e to the negative st dt. So again, it's a causal function. It doesn't turn on until t naught. So I guess I should have had that there. Yeah, probably should have inserted that unit step right there in the thing we're taking the Laplace transform of, just to make it more clear that this is a function that is not only delayed, but it's also delayed in terms of when it turns on. So this changes the lower bound of integration to t naught prime by looking at where the unit step is non-zero to infinity. Then we're going to introduce not a u substitution, but a gamma substitution. So we'll say gamma is equal to t minus t naught. So f becomes f of gamma. T becomes gamma plus t naught. dt becomes d gamma. And the bounds of integration, upper bound stays at infinity, lower bound becomes 0 minus. So this is how we move from the second line to the third line, is to do a gamma substitution with gamma is equal to t minus t naught. E to the negative s over t naught is a constant with respect to our new integration variable gamma. And then here we're left with something that looks like the definition of the Laplace transform, just with a different dummy variable. And changing the dummy variable doesn't change anything. So even though we're instead of integrating over t, we're integrating over gamma. No problems there. F of t minus t naught, again, probably with a little u of t minus t naught, equals, Laplace transforms to e to the negative st naught times f of s. With the same region of convergence as whatever f of s has. So let's look at what happens when we time delay some common functions. So if we time delay the unit impulse, and remember the unit impulse has a Laplace transform of 1, so we just need to multiply by e to the negative st naught, and yep, here we go. So this is a different function of s now, one that is, an exponential in the complex frequency land. If we time delay the unit step, when we're going to time delay a lot, we'll get e to the negative st naught over s. And then delay the unit ramp, we get e to the negative st naught over s squared. With the regions of convergence that matches the unit impulse, the unit step, and the unit ramp. Speak up if you have any questions. So multiplying by e to the negative st naught, not too bad of a thing to have to do. So time delays are pretty easy to handle. What about this? What if we multiply our function by e to the negative at? Well, there we're going to get integral from 0 minus to infinity of e to the negative at f of t e to the negative st dt. Okay, this is where there's like a lot of errors that I somehow did not catch when I was proofreading this. This should be the integral from 0 minus to infinity. So that shouldn't be t naught. It should be 0 minus to infinity of f of t e to the negative quantity s plus a times t dt. Remember, by exponent properties, the product of two powers is equal to the base with the sum of the two exponents. So e to the negative at, e to the negative st multiplies to e to the factor minus sign out, s plus a close quantity times d. We're going to do a lambda substitution where lambda is equal to s plus a. So we get that, this is equal to f of lambda. And this shouldn't be d lambda. This should be a dt right there. That's another mistake. So this should be 0 minus. This should be a dt. F of lambda. Well, we could just resubstitute s plus a in for lambda, and we get that e to the negative at f of t Laplace transforms to capital F of s plus a. So multiplying by e to the negative at in time is the same as shifting by frequency a or shifting by a in frequency. So the region of convergence is a little bit more complicated. It's the same as f of s, but shifted left by the real part of a. So it extends the extent as a is a positive number. The region of convergence gets bigger. If a is a negative number, the region of convergence gets smaller. And then one last property to discuss, and this is the Laplace transform of an integral. So let's say we have the Laplace transform of e to the negative at f of t. This one we're going to integrate from, or Laplace transform, I should say, of negative infinity to t of f of tau d tau. This is the integral from 0 minus to infinity of integral from negative infinity to t of f of tau d tau of e to negative st dt. So what we're going to do is do integration by parts. So we want to take the derivative of this. So this will be our u, and then this will be our dv. So integral of u times v minus integral of v du. But when we take the integral of this, we get a minus sign, so that changes it to a plus out front, 1 over s, and then we get this right here. This last term is pretty easy to handle. Look at this. We just get the definition of the Laplace transform. So this is just capital F of s over s. Now we need to figure out what's going on here. So when we plug in all t greater than 0, we're going to get 0. But we need to trim our upper bound to figure out what happened before then. So we're just going to get a 1 over s integral f of tau d tau when we plug in these limits right here, or these evaluation bounds right here. And we took the limit yesterday of e to the negative st over s as t goes to infinity. We figured out that it's 0, presuming that we have the real part of s greater than 0. So the Laplace transform of an integral is the same thing as f of s over s plus the integral of the function from all time from negative infinity all the way up to 0 minus divided by s. So it looks like the original Laplace transform divided by s plus a constant over s. That's the same thing as a unit step. So as a note, for this to work out, we must have f of minus infinity equals 0, and f of t converges to something finite as t goes to infinity. So that's just some notes. Yeah, this property, we don't like as much as the derivative property. That one's a little bit easier to deal with. I just kind of blasted you with some math. What questions do we have? Slide 22. Well, if you take the derivative of gamma, or you say gamma is equal to t minus t naught. So when you take the derivative with respect, if you differentiate both sides, you get d gamma is equal to dt minus dt naught. But dt naught is just a constant, or is the derivative of a constant. So you just get that d gamma is equal to dt. Does that help you, Aubrey? You're welcome. Any other questions? Again, you'll receive these properties in a table showing their proofs here for completeness sake and for your educational benefit, but don't expect too many proofs in your future. Let's see how we might use these properties. So let's look at our first circuit of the lecture set. So find the inductor current waveform IL of t in a parallel RL circuit that starts at rest. So IN of t is equal to delta of t. So okay, we have impulse input, and we have R and L. And from our previous investigation of the parallel RL circuit, we know that IN of t is equal to L over R DIL dt plus IL of t. Right, you should be able to derive this very quickly using KCL and the Ohm's law and the constitutive equation for an inductor. So let's look at how we might solve this problem. So 5-step process. So generate the ODE for the circuit, already done. Step 2, we'll take the Laplace transform of the circuit. So remember, the Laplace transform of, we use lowercase letters for the time domain, I sub L of t becomes capital I sub L of s. And similarly, the Laplace transform of IN of t becomes capital I sub n of s. So we get IN of s equals L over R times Laplace transform of derivative is s times I sub L of s minus IL of at time 0 minus, and then plus IL of s. But we can regroup this by factoring IL of s out of the 2 terms of the 3 that have it. And we get IN of s is equal to IL of s times quantity s times L over R plus 1 minus L over R times IL of 0 minus. The circuit is at rest, so IL of 0 minus equals 0. And we know that the impulse is the input. So we need to take the Laplace transform of a delta function. As we learned way back on slide 13, the Laplace transform of the delta function is just 1. So we get 1 is equal to IL of s times L over R times quantity s plus R over L. See what I did there? I just factored L over R out of both terms of s times L over R plus 1. So I needed to introduce the reciprocal for the constant term. So we can simplify algebraically. And I get IL of s is equal to R over L times quantity 1 over s plus R over L. And you can see now there was a good reason. We always have a good reason to do something like this, but we had a good reason to get 1 as the coefficient of our highest power of s. Should write down what I'm thinking right there so I know to say. The reason why we do it is because when we go back to our Laplace transform tables, when we take the Laplace transform of the exponential function, we notice we had 1 times s plus a, not factor of s plus, another constant b. So when we do this, we know, okay, R over L is just a factor. It's going to stick out front. But this is going to become an exponential function when we go back to the time domain. So it's going to be e to the negative R over L times t, u of t. And sure enough, that's what we get. And this matches the impulse response of the circuit. I guess one other thing to mention is that Laplace transform units, when you Laplace transform things, units become a mess. Usually you're off by, factors of time. So even I have a very hard time, and I try to be as meticulous as possible with my units. So you have to just check to make sure that your final answer and your starting answer make sense with units. What questions do we have? No, threshold not quite reached because I'm here. I want 30 students. There's only 29 students. So one more. Let's say we repeat the problem. Now, instead of the circuit starting at rest, we have a starting current in our inductor, some IL at 0 minus that is non-zero. So again, we'll generate the ODE. It'll take the Laplace transform. The circuit is not at rest and receives an input response. So we'll say 1 is equal to IL of S times L over R, S plus R plus L, minus L over R times IL of 0 minus. We'll simplify algebraically. So we'll get IL of S is equal to 1 plus L over R, IL is 0 minus. Divide by L over R is the same thing as multiplying by R over L times 1 over S plus R over L. So it'll match with the exponential function Laplace transform pair. You'll get R over L plus IL of 0 minus times e to the negative R over LT. So that was just, as we can see, we were able to do a completely different situation of circuit with the Laplace transform, and it wasn't that much harder. So, different situation, same steps. Laplace transform is nice. So let's do another example. So we're going to completely change our input. So find the inductor current waveform I sub L of t. Waveform only applies to functions of time. We'd have to talk about spectrum if we're talking about functions of S. In this parallel RL circuit that starts with IL is 0 minus not equal to 0 and has this B equal to negative R over L. This was normally the hard case when we'd worked with ODEs because we had B be the same thing as negative R over L, which was with the value of lambda from our characteristic equation. So that sort of repeated form of input for one of the natural responses normally caused issues. Let's see how Laplace transform handles it. So we'll generate the ODE for the circuit. Still, IN of t is equal to L over R DIL dt plus IL of t. We'll take the Laplace transform of the circuit. IN of S is equal to IL of S times S L over R plus 1 minus L over R IL of 0 minus. Circuit is not at rest, receives an exponential input. So how do we take the Laplace transform of this? I1 is just a constant. So it's going to be I1 times 1 over S plus B, or S minus B. But B is equal to negative R over L. So it's going to be minus a negative R over L, or S plus R over L. So definitely think your way through why this input has this form using the exponential function Laplace transform back on slide 16. Gotta be very careful with the signs. Normally we have a minus, we say negative AT up here, but this is a positive BT, but B is a negative number. So we can just think of it as 1 over S plus R over L here with the constant multiplier of I1 out front. So we do the same thing where we get a unit coefficient in front of S. So IL of S, L over R times quantity S plus R over L, minus L over R, IL of 0 minus. So we simplify algebraically. So we notice that this has S over R plus L in the denominator. We want to get other things to have that in the denominator. So we'll move this to the other side and multiply by S over R plus L over S over R plus L. And then we have IL of S is equal to things. Specifically, IL of S is equal to R over L. 1 over S plus R over L quantity squared. And then we're left with L over R, IL is 0 minus, times S plus I1 plus the L over R cancels the R over L, IL of 0 minus. So this is where you have to be good at your algebra. Again, remember that's one of the requirements for this course is don't get lost in keeping track of signs. Get good at algebra. So hopefully you can see how we move from this top line to this bottom line. If not in one step, then in however many steps you need to do it. So we can simplify further into Laplace transform pair forms. So yeah, right now we don't have anything that matches this sort of Laplace transform pair. So we can multiply through by R over L, and that annihilates that. We can factor out the IL of 0 minus in front of things. So we'll get IL of 0 minus quantity S plus R over L, quantity I1 over IL 0 minus plus 1, closed quantity, all over S plus R over L quantity squared, or IL of S equals IL of 0 minus S plus R over S plus R over L quantity squared, plus R over L, IL 0 minus, I1 over IL 0 minus over S plus R over L quantity squared. Finally, we notice that the S plus R over L cancels, so we're left with something over S plus R over L plus something else over S plus R over L quantity squared. So we know what this first one looks like. It's going to look like an exponential. This one is going to look like t times an exponential by our frequency derivative property. So we finally get IL of t is equal to IL of 0 minus e to the negative R over LT plus R over L times I1 times t times e to the negative R over LT, all times the u of t. That was a mouthful. There was a lot of steps in there, crammed to fit into one slide. However, you could see where we basically did the entire problem with relatively few steps, no calculus involved. It was just all algebra. No calculus, all algebra. And I thought I had a numerical example in here, but I don't, where I actually plug in numbers. So try example with numbers. Oh no, not algebra. Yeah, that was the whole bargain we made with the Laplace transform. All the calculus and differential equations goes out of view. However, we have to be good at algebra. Bound to make a side mistake in this? Yeah. Especially when you're doing symbolically. I had to double check my work a few times on this one. And the second last ILS expression, you see it. Okay. I guess for the benefit. Yeah. This one is just dividing through by S over R plus L in the first term. And then the IL of 0 minus cancels numerator and denominator of the numerator. Yeah. And everything works out nicely with units. Hooray. What more questions do we have? I know there's going to be questions later on, so if you don't have questions now, save them for tomorrow. That's okay too. Yep. We did this problem with differential equations. This was like lecture set 2, slide 50 something. There was like 11 steps. Yeah. You'll notice we've talked about parallel RL circuits before. There's just more steps to remember. I'll move on. So here we're going to talk about the most important property of the Laplace transform, why we're using the Laplace transform compared to anything else. And that's because we know for a fact that when we have an LTI system, the output is the same thing as the impulse response convolved with the input. So how does Laplace transform behave with a convolution? So, Laplace transform of y of t is equal to the convolution of two signals. So we'll have t integral from t naught to t equals 0 minus to infinity, integral of tau equals negative infinity to infinity, a of tau, b of t minus tau d tau, that's the convolution integral in brackets, e to the negative st dt. This outside stuff is our Laplace transform definition. So we simplify. So, okay, we just get a d tau first and then a dt. Then we're going to introduce lambda is equal to t minus tau. Thus, d lambda is equal to dt. So we'll get integral from lambda is equal to negative infinity to infinity. Integral from tau equals negative infinity to infinity. A of tau, b of lambda, e to the negative s lambda, e to the negative s tau, d lambda. Where, if we have t minus tau, notice tau ranges from minus infinity to infinity, so we got to change the lower limit all the way down to minus infinity, which normally that would be a bad thing. However, we notice there's a lot of symmetry to what we just stated here. We got two integrals from negative infinity to infinity. We got two signals multiplied by two complex exponentials, and then two differentials. Using the shadiest math I think I have ever seen used in an engineering textbook, we're just going to say, hey, we can say this is one integral, the tau integral, multiplied by another integral, the lambda integral. Normally you can't do that, but we're going to really go out on faith and say these functions are really well behaved, and for some reason we're allowed to do that. Your math professor would definitely frown if you did this on a math exam. So this is some really shady math, but this tau integral looks like the Laplace transform of A, and this integral looks like the Laplace transform of B. So we'll say that A of t convolved with B of t Laplace transform to A of s times B of s. And then we get the most important statement of our Laplace transform lecture set. So the convolution of time domain waveforms is equivalent to multiplication of frequency domain Laplace transforms. So convolution in time equals multiplication in frequency. This is a huge deal. Huge deal. And you can expect this to come up. Yeah. So the multiplication is the operation that corresponds to convolution in one domain versus the other. So speaking of one domain versus the other, we have to talk about time frequency duality. So we've encountered properties that are mathematical duals of each other. So the time derivative property where d dt of f of t becomes s of f of s minus f of 0 minus, and the frequency derivative property, when you, instead of multiplying by s, we're now going to multiply by t in the time domain, and that's equal to negative dds of f of s. Okay, that's similar properties. The time shift property, if we delay a signal by t naught, that's equivalent to multiplying by e to the negative st naught. And the frequency shift property, if we multiply a signal by e to the negative at, that's the same as shifting forward by a frequency a. We have the convolution property. A convolved with b in time is equal to a times b in s. And we have this new multiplication property. If we multiply two signals, a and b in time, that's the same thing as convolving a and b in s. So if you look closely at this property, when are we ever multiplying two signals together? And you might remember, okay, power is equal to voltage as waveform times your current waveform. So that says, hey, if we want to get the Laplace transform of power, that's going to involve a convolution in the S domain. And we're trying to avoid convolution because we said it was getting messy. So Laplace transforms are not meant for power calculations or for energy calculations. Remember, like the energy in a capacitor is 1/2 CV squared, where V squared is just V of t times V of t. So that means, we have to convolve a signal with itself in frequency if we were to work with an energy calculation. So power and energy calculations are not meant for Laplace transform. They don't make those any easier. So you've been warned in case this comes up later on in your careers or if you decide to do research. But the main point here is duality. All these properties kind of seem to have a, counterpart with each other. Time derivatives, frequency derivatives, time shift, frequency shift, convolution, multiplication. Manipulation in either domain produces equivalent changes in the other domain that can be used to solve twice as many problems as before. So if you know how one property works, you can figure out how the other property works by duality. Time and frequency are duals of each other. Mind blown. Questions? Here are no questions. We're going to have to do something that is, horrifying to behold. We'll have to talk about the inverse Laplace transform. Now, the Laplace transform itself wasn't too bad. So why is the inverse Laplace transform that bad? So while we need the inverse Laplace transform because we ask questions about time domain things and we want to answer them with time domain answers. So if we're using the Laplace transform to get to the frequency domain, we need a way to go back from the frequency domain to the time domain. And that is the inverse Laplace transform. So we'll say x of t, our time domain signal, is equal to the inverse Laplace transform. That's our calligraphic L to the -1 of, in curly braces, x sub x of s, where x is capitalized to denote that's in frequency. And that is equal to 1 over j times 2 pi times the contour integral over a specific contour capital gamma of x of s e to the positive st ds. And you should, tremble in fear when you see this. If studying the derivatives of the delta function is the path to insanity, this is just a horrifying sight, is the inverse Laplace transform. So it would take about a course of complex analysis to understand exactly what contour we're supposed to choose, capital gamma, for this, contour integral over a closed path. Because you have to be specific about, lapping around the origin and all sorts of other things that I don't fully understand because I never took a course on complex analysis. So, we are never going to use this definition to do an inverse Laplace transform. Instead, we'll just play pattern matching in the Laplace transform table going forward. So in order to solve problems, you will be, provided with a Laplace transform table. That is how we're going to handle these sorts of things. Especially on exams, you also need a Laplace transform table in order to do your homework. So, we're not going to use this definition I don't think most of us could do it correctly, even if we tried. So we're going to resort to using, just table and matching patterns rather than any sort of formal proof. This is not confusing at all. I totally understand that completely. Riyadh and Aubrey, you can totally try to use the inverse Laplace transform in the complex plane with a contour integral. See how far you get. It is going to be harder than you think. So we'll not get through all of this next part, but we'll at least get through one or two cases. So okay, we said we need a pattern match if we're going to use the inverse Laplace transform. Now, technically, the Laplace transform could be any sort of function of S, but since we work with physical systems that are usually stable, we're going to get rational functions for the frequency domain. So this kind of goes back to pre-calculus where we talk about rational functions. Remember, rational functions are, two polynomials divided by each other. So we'll get f of s is equal to a sub m, s to the mth power, plus a to the m minus, or a sub m minus 1, s to the m minus first power, plus all the powers down. So we get to a1, a sub 1, s to the first power, plus a naught. All of that over s to the nth power, plus b to the n minus, or b sub n minus 1, s to the n minus first power, plus all the way down to b sub 1, s to the first, plus b naught. Where here you'll notice that we don't have a coefficient in front of s to the n. If we did have one, we would just divide, factor it out, divide through everything so that, we'd have the coefficient be in front of all of the a's instead, built into the a terms, not into a sort of b sub n term. We want b sub n to be equal to 1. Now, we can factor the bottom polynomial, and we'll pull out what we call the poles. So s minus p sub 1, s minus p sub 2, s minus p sub n. Poles just being the roots of the denominator of the rational function. And then we can simplify this further. If the power of m and n are equal to each other, we will get this factor k when we do polynomial long division. Otherwise, if we usually deal with n greater than m, and then we'll just get terms that look like this: a1 over s minus p sub 1 plus a sub 2 over s minus p sub 2, all the way down to a sub n over s minus p sub n. How do we get there? Using everyone's favorite tool, partial fraction expansion. So we go from a ratio of polynomials where, we've got this large, nasty polynomial to a whole bunch of simple rational functions like this, where we know what these look like. These look like exponentials in time in the Laplace transform table. So we set under normal conditions, m is less than or equal to n, denominator factors like that. So wherever the denominator equals 0 identifies the poles of the Laplace transform function, so the p sub I. So again, these are called the poles. As a trivia for right now, the roots of the numerator polynomial are the zeros. They're called the zeros. So this sum of simple terms can go through the inverse Laplace transform table to get the time domain signal of interest. We couldn't put this big polynomial rational function through the inverse Laplace transform table and expect to get anything out of it. We're only going to get terms that look like this that can go through our inverse Laplace transform table. So there are 4 basic cases, arguably 6, that we need for the roots of the denominator of f of s, which are analyzed on the following slides in finding k and a sub I. How are we feeling about partial fraction expansion? Everyone excited? I know this is everyone's favorite part of mathematics. Height. Laplace transforms can be satisfied. Yep. And frowny face. Okay. So we'll look at rational function case number 1. So if we have distinct real roots. So the condition for distinct real roots in the denominator, p sub I not equal to p sub j for all I not equal to j. So here we're just saying, okay, P1, P2, all the way up through Pn are all different numbers. And they're all different real numbers. So the inverse Laplace transform of a constant. So we have this constant. Its inverse Laplace transform is just k times the delta function. The Laplace transform of a linear term reciprocated. So if we have a sub j over s plus a, that Laplace transforms to a sub j e to the negative at u of t. Or if we just have a over a sub j with s, but there's nothing being added to it in the denominator, it's just aj times u of t. You know, we can say that the step function is basically an exponential just with a equal to 0. That's kind of what the inverse Laplace transform table is telling us. So some of you may have heard of tricks called like the Heaviside cover-up method to get the coefficients k and a sub I quickly. I'm not going to do it the first time around. I'm going to do it the formal way to get Laplace transform. So here we're going to have a function f of s is equal to s squared plus 6s plus 2 all over s cubed plus 11s squared plus 31s plus 21. So with the rational root theorem, we can say that all our roots are going to be plus or minus 1, plus or minus 3, plus or minus 7, or plus or minus 21. And we can try each of them and factor them out, do polynomial long division to get what's left. And we'll get that we'll have s plus 1, s plus 3, and s plus 7 are our factors of this cubic polynomial. Now, we're going to put it into the form of this. So we're going to say the form is a1 over s plus 1 plus a2 over s plus 3 plus a3 over s plus 7. You must get the form correctly if you have any hopes of getting the right answer. So we'll just say this is the sum of all of these things, where we have each a sub I over each of these factors in turn. We're going to multiply through by this denominator and clear the fractions. So we'll get s squared plus 6s plus 2. The s plus 1 will cancel. We'll just get a1 times s plus 3 times s plus 7. The s plus 3 will cancel out, so we'll just get a2 times s plus 1 plus s plus 7. And then finally, we'll get a3 s plus 1 times s plus 3. So now we're going to evaluate at the places that make some of these terms disappear. So we're going to evaluate at s equals minus 1. So when we evaluate both sides at s equals minus 1, notice that this term becomes 0. So we'll get a 0 for this second to last term. This last term is going to have a 0 right here. So we'll get a 0 right there. And then we'll get, for the first term, a1 times negative 1 plus 3 times negative 1 plus 7. And then on the left-hand side, we'll get negative 1 quantity squared times, or plus 6 times negative 1 plus 2. We can solve this for a1. a1 is equal to 1 minus 6 plus 2 all over 2 times 6. That's negative 3 over 12, or negative 1/4. We could do something similar to get the other coefficients. Actually, let me just pause a moment, just appreciate what we did. So let's pause a moment, appreciate what we did. We took, after we cleared the denominators of both sides of our equation, we found a1 by choosing specifically the point that made all of the other terms disappear, so that we could solve for a1 in isolation in the single step. Because, you know, this equation must hold true for all values of s, including s equals negative 1. And that allows us to solve for the first term. If we want to find a2, we can make the other terms disappear by choosing s equals negative 3. So when we choose s equals -3, we get 9 minus 18 plus 2 over -2 plus 4, where, -3 plus 1 is -2, -3 plus 7 is 4. We get plus 7/8. And for A3, we can solve for it basically by choosing s equals -7. When we choose s equals -7, we get 49 minus 42 plus 2 over -4 times -6, or is positive 9 over 24. So now we have the A1 and A2 and A3 that go into this, so we can plug them in. So we get f of s equals -1/4 times 1 over s plus 1 plus 7/9 of 1 over s plus 3 plus 9/24 of 1 over s plus 7. We know the inverse Laplace transform of this is just e to the -t. This is just e to the -3t, and this is just e to the -7t. And then we introduce a u of t. That comes from our Laplace transform table as well. And we get this final equation for f of t, where I put some text down here that explains exactly what we did. And if we wanted to find k, if there was a k we needed, because let's say this was s cubed over s cubed terms, there'd be a k involved. We can always just choose s equals infinity to find k. That's allowed. Cool question. And then, as a little homework assignment for the class, I encourage you to look into the Heaviside cover-up method, which is an even faster way to find partial fraction expansions. We're going to be finding partial fraction expansions for the rest of the semester. Problem 3 got your brain smoking. Hopefully in the good way, where you're clearing out any sort of particulate gunk in your brain so that it can run smoothly. Yeah, sure. Any more questions? I don't think we ever reached our threshold voltage today, but I'll go ahead and dismiss class. Goodbye, everyone. I'll see you in office hours starting at 11:30. You're welcome. Goodbye. Goodbye, everyone. Bye-bye.